amount sensor, then it's not accurate. But if you buy, for example, other sensors, so-called the LiDAR, then a couple of $100, then it is really accurate. All such things. So sensor may determine the quality of the services, right? But whole purpose of this project and this class is not the accuracy or qualities. Quality and accuracy may be determined by your investment money, right? I'm not sure why somebody. Try to log in. This is not really. Okay, I'm not. All right. So. Choosing a topic for your project needs time and needs your efforts. You have to think a lot. You have to. Another way that you could do is to read some articles. Then you may be able to get some clear idea what you want to do. Some typical tedious project topics could be, because in the previous classes, many students try to do tour guide. Okay, you can. User of that app may take a photo and save it and make it available for other tourists, or some reservation apps. Many such things are available. It is very typical. You can retry to build your skills. That's fine, as far as your project complete. Complete doesn't mean that it should be huge and perfect apps. Some scenarios needs to be fully exploited. I already asked you to do homework assignments posted, or
the one due next week.
Yeah. So while you are completing that homeworks, you may feel, oh, this is what I want to do. As I said, be ambitious. Do not squeeze your project small enough for you to accomplish. But I want to make it bigger. And that is not a project proposal yet. I want you to think big picture first. And then when I ask you to submit a project proposal, then you can do something that you could do by the end of this semester. Okay. To make things sensible, then we have to consider sensors, right? Why sensors? Basically, to overcome the limits of human senses, human capabilities. Human has 5 senses, right? As that you can see on the slide. Touch, there's a sensor. Touch sensor, lots of touch sensors are available. Usually, we do not use it, but let's talk about door lock, because that is the project that I am doing. I'm trying to commercialize it. But anyway, door locks. Then when door closed, then there should be some touch sensors so that door is touched to the door frame, and then by some codings, door is locked. Then it is a complete locked, right? So that things needs to be done. Touch sensors, from my survey, cheap ones, a couple of $10 or $20 sensors, but real sensitive touch sensors, I think $500. Something manufactured, for example, in Japan, then very, very expensive. Okay. Of course, in your home door, you don't need to invest $500 touch sensor only, right? If there is a 500, then lock itself could be very, very expensive, right? From my survey, the most expensive door lock, guess what? How much? Have you purchased the door lock in Home Depot? Yeah, lock
Yeah.
that whole body. If you go to Home Depot, if it is not electronified lock, only mechanical lock, then maybe $50, right? But hotel locks, if you go to hotel, some good hotels, then they usually install minimum $1,000 lock. Some company in Connecticut, they produced the locks, and they installed the lock in some U.S. government, including White House. How much they sell? The lowest, the cheapest lock they sell is $10,000. One lock, $10,000. If there's a $10,000 lock, then touch sensor could be $500 worth, right? So if we combine all high quality sensors and locks, then it could be $20,000, $30,000. All right, there's a touch sensors. So sensor that we have very good sensors, right? Our fingertips, then we feel something, right? We feel, if this is a fruit, or this is a metal, or plastic, or some liquid, we can feel it. But if you install some other electronic sensors, maybe much more sensitive and accurate than human sensors. But relatively, compared to other sensors, human touch sensors may be much better. For example, hearing. Our hearing is not really good enough, right? If you raise doggies or some animals in your home, then doggies can hear something human cannot, right? Therefore, they start barking when something happens, although we don't feel any. So hearing. And also when human is aging, then hearing capabilities may reduce a lot. So your grandfathers cannot hear much, even if you shout, right? Hey, grandma! Your grandma don't respond, right? Taste. Each one has different capabilities of tastings, right? Some some bodies, for example, if you go to some restaurants, so my friends loves all kinds of foods, but some other friends do not want to eat. Why? Why that happens? Somebody loves to eat any kind of food means that person does not have sensitive taste. Okay, so so they eat, but some small babies, they reject some food, right? Because they are sensitive. They have brand new taste. But at our age, we love any kind of food, right? Sometimes we love spoiled food as well. Therefore, we have some stomach ache. Sometimes. Sight, eyes, all that is important, right? In this room, 75% wear glasses. You are the only one who do not, right? Do you have a contact lens?
No.
Right. You're good, right? What about your father and mother? They are still as good as yours, or it's aging, right? Yeah. Right. Sight sensors is not really reliable. It depends on our ages. Smell. But anyway, the sensor devices can cover much more than this. We don't feel some of the waves running here in this space, right? Anybody can catch radio waves so that you can tune some radios, some TVs? No one's, right? That's beyond our audible or acoustic frequency ranges. It's far beyond. So human sensors are not always functioning. Human sensors are not enough to catch. So sensor technologies, sensor engineering can develop unlimitedly many sensors, various frequency ranges, not only very low frequencies, but high frequencies. Anybody can see or hear X-ray frequencies? No, right? You cannot even expose yourself in front of X-ray emitter. Then your cell burned, right? Therefore, if you take X-ray test, then usually you need to protect all others, but open only that spots. And also X-ray should be very, very short time of exposures. X-ray is beyond the frequency range of our visible frequency range. The high frequency of visible frequency range is purple. So above that is called ultraviolets, right? Violet is a purple, so ultraviolets. And then lowest frequency of visible. If you think of the rainbow colors, then lowest one is red. So the frequency lower than red color frequency is called infrared. Infrared is lower than red color. So our sunlight color frequency range is really, really high frequency. If waves in high frequency, then it carries higher range. So under the sunshine, if you are exposed to purple highest frequency range of the sunlight, then your skin will be burned, right? So there's ultraviolets. Red ones may be okay, but altogether, your skin may be burned. Higher than that, for example, X-ray, it kills all of your cells. It can burn your, depending upon the strength and density, X-ray may reflect from bone. So if the doctors identifies your bone skulls of your bodies, then they take X-ray photos, right? Because it reflects from your bone. When you walk through the airports, airports scan whole body of the passengers, right? It is not high near the X-ray frequency ranges. It's a little lower, but that is higher than our sunlight waves. What that means is that it can reflect anything in your bodies if you possess, but it doesn't hurt your human skin cells. Okay. So various frequency ranges. I may, on some slide, if we use a laser, the given waves from acoustics, some hearable wave, our sonic, the waves that start from 1 hertz towards 20 hertz or 20,000 hertz, and then it goes up to ultrasound frequency, and if it goes far beyond, then we have a microwave frequencies. Our cell phone is in that range, microwaves. So 2.4 gigahertz, 2.4 10 to the power. Gig means, I think, 9 hertz, right? And then it goes up beyond and above. Then we have the sunlight's visible frequency range. Above that, we have ultraviolets. Above that, X-ray, gamma ray. All those things are already exist. But there is another waves invented by human that is called the laser. So laser is a human invented waves. What that means is that frequencies may vary depending upon our design. Before I forget, I'm going to add these things also. The visible frequency ranges, LED light, that is also human invented. So LED originally was invented a light LED, red light LED first. Now all different kinds of colored LEDs possible, right? That is also invented by human. Laser, LED is a limited frequency ranges. Laser, wide ranges. So we can tune the frequency ranges. As I said, if it's very high frequencies, then it has really high the energy. If it has big energy, then it can travel a lot, right? If you compare AM and FM frequencies range is a lot higher than AM. So FM goes too far, but only the issue is it doesn't bounce from the landscapes. So if there's open space, then FM can reach further. So likely laser, depending upon the frequencies, it can reach long distance. So when we send air shuttle to the moon or Mars, any other stars, how can we communicate with space shuttles? Usually in the concept of laser, so they can go further. So various frequency ranges. IR sensor, one of them is the IR sensor. IR stands for infrared. As I said, that is a little lower frequency than visible light frequencies. Sunlights, if there is a light, then the frequency in that range. Outside of that range is dark. If it is dark, it doesn't mean that nothing exists, right? So if you have an infrared camera, then it can take some objects even dark at night. Camera lens technologies developed for long decades in few countries, like German lens, Japanese lens. I think those two countries are leading the camera lens. Lens itself is not really sensitive to frequencies, right? Because that is simply some of the physics mechanics, right? So in order to improve the quality of images, what they did was they put the filters so that they want to filter out some other frequency ranges. Only include the frequencies where there is the visible, clear colors. That is our visual frequencies. What that means is that it filter out something that we cannot see at dark nights. That is what the camera lens developed currently. For some purpose of the military, the military wants to see something at dark nights, right? Because a war is not allowed only daytime. Maybe ancient time, a long time ago, right? Then only soldiers can move when the sunlight is available. But current, the military technology is not really under the sunlights, even dark at nights, 24/7. They need to see what object is available in front of us. Then IR camera is needed. So what they did is that the current lens filtered out IR or ultra frequency, infrared or ultraviolets, that range. Outside the ranges are all filtered out. That is in that way we can get the clear pictures. That is what camera lens can do. If camera lens does not have any filtering additions, filtering capabilities already added, but if we take that out, then we can still observe all the ranges. Then we can see some object at dark nights. Then IR camera needs to be cheaper, right? Actually, that was cheaper. But in the markets, IR camera is a lot more expensive because there's a supply chains, right? If you can test that if you have some of the cameras, old cameras at home, then if you look inside, then there is some of the extra filters in it. If you remove that extra filters out and take a photo, then you can, that is IR cameras. Then you can take a photo even at dark nights. Okay. IR sensors. Laser sensors. Sensor is a device that is to detect events or changes of objects and provide an output. So sensor is nothing but transducer. So there is an input energy, and we expect output energy. Input energy could be, those energies could be electrical energies, or magnetic energies, optical energies, thermal energies. Many different energies available. So definition of transducer, as I said, that is a device that converts one form of energy to another form of energy. So that is a transducer. I think we have anybody's. I think last week we had somebody with the undergraduate in electrical engineering, right? Are you electrical? No. But anyway, if somebody's doing electrical engineering, can you sign in there?
Sure.
But anyway, then they learned transducers. Transducer nothing but the device that can convert from one form of energy to another form. Okay. So that is exactly the sensor comes from. So example of a transducer or examples of sensors that we can see: generator. You know generator? Electric generators, power generators. So if we do not power outage, then we start generator. The motor runs. In order to rotate the motor, we may do some gasolines, or maybe humans rotating. If we do this very fast, then it generates some electric powers, right? I'm not sure you guys picture that, but when I was young, in militaries, there's a military phones. Military phones can generate the power by rotating the phones. If they rotate this very fast, that it generates the power so that it can generate wireless signals to the long distance. That is what military devices. Because military do not expect consistent battery supplies, right? So motor can convert it to electricities. Of course, electricity can convert motor spinning. That's what we do usually, right? We we supply power, then the motor runs. Motor is circularly runs, right? Almost all the robots and always all the man-made objects to move. So move, then it moves forward and backward, right? Move. It starts from the motor. Motor runs. Motor is circular. That can be the movement direction may be converted to horizontally, so that robots can move. But inside, motor runs. As I demonstrated last week, door locks, for example, then there is a bolt locks side. So bolt locks goes out, so lock the doors. Then this is a horizontal movement. To make some bolt moves horizontally, motor runs inside. Motor should runs, and that the direction may be converted to horizontally, so that it pushed back and forth. But anyway, so a lot of transducers available. Question?
What's the difference between transducer with sensor?
Transducer is more global terms. Global terms. Some of the concept of the sensor technology is a transducer. Transducer is changing from one form of energy to another forms. Sensor is a limited versions. Some special form of a transducer is called sensors. So we're looking at sensors only. Transducer is a more wide ranges, global terms. Battery is another transducer from chemical to electricity. This is the batteries, right? Battery is so hot these days. Why? So battery powered devices are well demanding, right? If you see, for example, automobiles, right? Car, then battery-driven cars. That is, for example, Tesla, rather than from gasoline to car movement, but the Tesla has from battery to car movement. If you look at the battery inside, typically there is some chemical components filled in, and that chemicals is drained out. Then a battery is expired. But now batteries has been developed, and the inventor of that batteries, there's a new revolutions. I think 3 people got Nobel Prize. They are chemistries and physicists. 3 people, I think about 3 or 4 years ago. So they developed the lithium batteries at that time. I think one of those guys is a Japanese. He worked for Toyota Motor. His chemistry. But anyway, that's a lithium batteries. Now, battery technologies becomes very, very hot, so many countries try to develop new types of batteries these days. They try to cost down and make the batteries to last longer and longer. These days, batteries doesn't last long, right? Even if we recharge it, then it doesn't last 24 hours. Like our cell phones, so batteries in it. My cell phone, that is 5 years old. The model X, iPhone 10X, right now 15, right? So 5 versions behind. So battery is almost outdated. So how many times that I need to charge? I need to charge it at least 3 or 4 times. If fully drained, if I use 2-3 hours, then I have a recharge and recharge because it's 5 years old. I want to replace that with iPhone 16. 15 was in the market last fall, right? If I wait maybe 8 months more, then I would get new models, 16s. Or if it dies before my plan, then I may get the 15, version 15. Light bulb, electricity can be converted to light or heat. There's a heat generation light bulb, or light itself generations bulb from electricities. Electromagnetics, input is electrics, output is magnetic. Do you see these days, if you go some buildings, some door, it is electric, it is a magnetic pushed, right? You cannot open it. It's very, very hard. The magnetic touches, then you cannot detach it. That's very hard. What is the source of that magnetics? Electricities. So if you turn off the electricities, then you can open it. If you supply electricities, then it is like a glue, perfect glue. Electromagnetics. Speakers, input electricity, but output maybe sound. There are so many different types of energies to be converted to another type. All those things can be called, that concept is called transducers. And most of those are also manufactured as a device. Then we call it sensor. And sensor may be embedded in so many electronic devices. Home appliances, you see a lot of sensors there, right? Refrigerator, for example. If you open the refrigerator doors, then touch sensors there. It can identify if it is untouched longer, then it gives you some alarm, right? Ring bells. Lots of the advanced home appliances include more and more sensors. So our humans do not need to worry about, we do not need to open our ears, open our eyes, because there is some sensors that can tell something to us. Now, more specifically, let's consider sensors. That is a passive sensor and active sensors. We need to think of two different sensors. Passive sensors, sensor itself do not need to anything because the object can generate some waves. So passive sensors simply receive it and sense it. That is a passive sensors. On the other hand, the active sensors, the object may or may not, even if it emits some waves, if it is not really significant, then transducer itself needs to send out waves and received reflected waves from that object and identify what that object is. That is active sensors. Example of passive sensors. For example, temperatures. Although it touches our bodies, the typical body temperature the device, then we can place into under the tongue so that that device tells the temperature of our bodies. That is a passive. That device, if you see that device, the device does not do anything. But another type of device, temperature sensors device. That was very popular during pandemic. That is so-called IR, infrared temperature sensors, or ultrasonic temperature sensors. So what they do is they have a gun, and they trigger. Then that waves goes to our head, and then reflect it. So take that reflected signals and measure the sensors. Okay, that is what they do. That is active sensors. Speed gun, that is active sensors. Image detections, usually active sensors, right? But there is a passive sensors as well. We call that thermal images. Thermal images. Our human body or any living objects, then it has its own body temperatures. That from that body, the heat's out, right? Thermal. So that take that heats, and then we can see the shape of the bodies, or we can measure which part generates more heat than others. So if I have that sensors, that sensor is expensive. It's about $300. That one device. It's like a camera, but it doesn't take your colorful the images, but it takes thermal data only. Usually from our head, more energy, more heat is generated compared to our chest or shoulders. So that we can see it here is a dark, it's red, and the others maybe blue. During COVID-19, if almost all the airports, if passengers comes out, then they check the thermal images and see which one has right now high fever. Then high fever. If some passenger says a high fever, then they select that person for the diagnosis. That type of things is a passive, because the living objects, living animals generates some heat, some temperatures by itself. So device simply receive the temperature data. That is a passive. Now you see the passive and active sensors, right? So difference. Okay. So this is another explanations of active and passive sensors. There's a stimuli to the sensors. How we can acquire sensor data. If it is active sensors, then we need to generate something first, some stimulates, right? So acoustic stimulus, electric stimulus, magnetic, optical, thermal, mechanical. We're not going to go further in detail for this, but you can, if you are interested in, you can read it. For example, to select a type of a sensor that you want to find. If you see the mechanical sensors on the bottom row, then accelerator, there's a sensor, force sensor. If we push, then it can identify. If you touch, then that is touch sensor can identify whether it is touched or not. Press sensor, like force sensors, touch doesn't care. But if you press it, then it identifies. There's a force sensor, stress sensor, pressure, strain, mass, density, movement, torque, shape, roughness, orientation, stiffness, compliance, crystallinity, structural, thermal temperature, flux, specific heat, thermal conductivity, optical, something that we can see, wave velocity, refractive index, emissivity, reflexivity, absorptions, magnetic field. Magnetic field, therefore, we can see NFCs. You see it. NFC stands for near field communication, right? One of the near field communication is called RFID, radio frequency identifier. RFID is something that you, if you go to a hotel, not far advanced hotel, but hotel, then usually when you check in, then that gives you a card. Card is your key, right? Longer time ago, then they gave us a real key, a metal key, so that we open the door. But now they give us small credit card type of keys. That is magnetic. Little further range of the communication, possible communication of NFC is so-called EasyPass, if you drive, then EasyPass can be charged by toll fees automatically as you pass. Then how that EasyPass can be identified, then there is a RFID reader. You see it on the highway, then there is some blinks over the bridges. That is the reader, RFID reader, that's send out some of the signals. Then your car needs to have a card that is called EasyPass card, right? EasyPass card there on your dashboard of your car. Then it identifies the ID of that card and charge it to your credit card, right? Lots of sensors available. So this is another picture that that we can consider. So like a big picture. There's a targets, some objects. There's a controller. This controller is what we need to do in this class. We're going to use a microcontroller, particularly Raspberry Pi. On the Raspberry Pi, we need to do some small program, and that Raspberry Pi has a pinouts. So through that pinouts, we can wire the sensor. That sensor is functioning. Sometimes we need to calibrate. If you want to see motion detections, then usually that motion detection sensor has a calibrator. So how sensitively you need to sense the motions. After that, we can collect the sensor data. If action is required, then we need to actuate it, actuating some of the response. Usually, if there is some force related on that actuation, then as I said, usually the motor should be spinned. And then from that motor spinning, we can convert it to whatever the direction that we want to do, right? If we want to activate robots by sensing, then the robot has lots of the motors running inside. So we need to actuate that motors. So all of these functionalities on this controller needs to be or can be done on Raspberry Pi, and the program running in that Raspberry Pi. Raspberry Pi is nothing but small Linux operating systems. So if you guys has a Linux OS experience, you will love it. If you do not have any experience, don't be scared. Take this time to experience about Linux operations. So I'll let you know some of the command so that you may be able to do it. On Raspberry Pi, the language that we are going to use is Python. Okay, Raspberry Pi Linux operating systems include Python by default. Unless you try to use a C language, the Python is enough. So that's That's what this wireless sensor networks was. So there is an object. That object's behavior needs to be sensed by controller, more specifically microcontroller. Device for that is called Raspberry Pi. So Raspberry Pi, that's nothing but Linux operating systems. Very, very cheap Linux operating systems. We need to program it and do some actions against that target objects. Our project, as I said, this is optional, but the other components, there is iPhone apps, right? App developments. This data, sensor data needs to be posted on the cloud server. Cloud server, all the information will be given to you, also demonstrated here, so that that server side, the systems already defined, so that you can simply use it. This is some of the spectrum of the frequencies, waves. Bottom here, we have 10 gigahertz or 100 kilohertz. They are all in the range over here, so-called the microwave range. In microwave, there is a radio wave, AM radio, FM radio, TV ranges, a little further, micro oven ranges. So that is up to this. Up to 10 gigahertz. Our cell phones uses 2.4 gigahertz frequency ranges, somewhere here, right? So that's somewhere here. That is exactly microwaves. Above this, if you see the energy itself, then this is tanning booth. X-ray is far beyond, far above, way above here. I've never been in tanning booth, but some ladies, right, do that. Maybe hot inside, right, in the tanning booth. Anybody has experienced a tanning booth? But anyway, I think it is hot, right?
My friends are from.
Yes, some heats inside. X-ray is higher than that, and gamma ray even higher. Lower than the frequency and wavelength, they are correlated. So if you have low frequency, then wavelength is bigger. If it's high frequency, then wavelength is very, 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 very short. How short it is? 10 to the power negative 12 meter. What is the wavelength of, for example, our acoustic wave, our sound? Then that is like kilometer. Somewhere here. Megameter, kilometer. Static field. So this side is a low energy, low frequency, high wavelength. The other side, high energy, high frequency, low wavelength, very, very low. See here, X-ray and gamma ray. If our human body is under X-ray, then our bone, the iron, so broken bonds. Some of the bonds, cell bonds, may be broken. What that means is that our human cell, skin may be burned or killed, died. Okay, example of sensors. So federal projects available and academic projects and commercial product. The other projects. Let's take a look. Short, some very long. So we do not need to stay longer, but I will point to you guys.
March 16th, 2018. The U.S. government's Defense Advanced Research Projects Agency, commonly known as DARPA, announces a bold initiative to develop what they call next-generation non-surgical neurotechnology. It is designed to allow the human brain to directly interface with machines.
We know that DARPA is exploring human-machine interfaces that include direct connections between the brain and outside systems. That's been from the beginning of DARPA's information technology mission, and it continues to this day. DARPA has created some of the most influential technologies of all time, things that we use and take for granted every day, including the project that became the internet. They've created self-driving cars, stealth technology, GPS that fits in your pocket. That's DARPA's specialty, to imagine the future and create it.
A new technology that is actually very much on the verge of being a reality that is being fielded is we could have a sensor maybe on the surface of our head, or maybe implanted somewhere in our body, in our brain, or something that allows us to interact directly with our communications gear, our processing gear, our weapon systems, and so on. Now imagine we take that technology and we can control robots at a distance with it. Even fly drones. You put this sensor on and you think the right way, and you can increase the speed of the fan by thinking and controlling that thought with direct-to-mind or mind-machine interfacing. With that type of capability, you could control all sorts of buttons and mechanisms in equipment.
Mind-machine interfaces will have many applications in both civilian and military life. But there are those who believe that this same technology could also be used by DARPA as a new form of mind control. Like their counterparts at the CIA, DARPA-funded researchers have spent decades investigating how the human mind can be altered. In 1965, DARPA launched Project Pandora, which studied the possibility of using microwave radiation to control human behavior. The project reportedly ended in 1969, but DARPA's investigation of how machines can affect and possibly control the brain continues to this day.
There are explicit programs of DARPA to read and write to human brains, whether it's through direct implants within the brain or wearing some kind of cap. So these things are being worked on, and we know that.
So what's the next step? Maybe the next step is we can send instructions and information to an actual person from a distance with this kind of technology to let another person control their actions. But that could be something that could be malicious.
If there's some way to do it from a distance, a much greater distance than something that you can wear on your scalp, that would be the ultimate technological achievement that would fall into this realm of mind control and direct human-machine interface that DARPA may well want to keep secret.
In the near future, DARPA may possess the technology to remotely control the human mind. But as concerning as that may be, according to some scientists, a more permanent kind of mind control technology is looming. And it involves modifying the human brain by altering the human body's DNA.
The future of mind control, and the future being right now because these experiments are being done, is using gene editing tools. And one of them would be CRISPR. The way it works is take the CRISPR, which are these short alternating repeats of DNA. You put that together with an enzyme called Cas. And so you take the CRISPR that you want to use, and you put these pieces together that can be injected and insert this DNA to certain areas of the brain so that we can change brain cells and turn you into something you wouldn't otherwise be. So in this way, gene editing technologies like CRISPR really form a definite basis for future mind control.
These are things that DARPA has investigated. Every technology has the potential for good or evil. And who defines what's good and what's evil, and who uses it for what purpose? These are all questions that have been asked about everything from rockets to self-driving vehicles. We still don't have a good handle on the ethics of various technologies that we use. The technologists tend not to be so concerned with the ethics. That seems to be the domain of other people, policymakers, for example, academics, people like this. There needs to be a hand-in-hand interaction with people creating technology and those who are considering the ethics of that technology.
Interesting, right? Scared? When was it? About 5 years ago. What about now? High advanced, right? I guess. So
60 minutes. Rewind.
Have you ever wondered if all those people you see staring in...
Okay, next one is academic project.
This project started because the government was interested in developing better ways for us to connect to the brain. So we have this massive amount of data coming in, massive amount of data trying to go out. And they've been thinking, how can we make it more efficient for us to communicate? Normally, when we think about tapping into people's brains, we're like, whoa, hold on a minute. Like, I don't want to have some kind of surgical implant or microchip or something like that. And it's really not a viable way forward if we're just talking about a healthy subject or a healthy person, a healthy soldier trying to control his or her drone better. And so, given this fact that we want to be able to communicate more quickly with our external device, we don't want to have surgery. Can we come up with a non-surgical way, an external device, a helmet, a hat, that would allow us to capture signals from the brain and stimulate the brain as though we were sitting in front of a monitor? And that's the big idea, this non-surgical neural interface. So it sounds a little wacky. Is this even possible? And so we began by simply looking at what are the physical processes we could use? What are the techniques that might give us the ability to communicate with the brain through the skull? So we started this in a very exploratory phase, and we looked at how we might be able to use magnetic fields and how we might be able to use light. Both of these things can penetrate the skull, and we wanted to understand if signals from the magnetic field and from light would allow us to record and stimulate the brain.
As the magnet turns on, the flies are stimulated, so we're working to stimulate their brain using nanoparticles that I've already injected into the flies.
So when people hear about programs that are designed to build a brain interface, particularly programs funded by the government, people naturally get concerned. And what I want to make clear is that the systems we're developing are really designed to help patients. You know, the long-term vision is that maybe these technologies could help people who are healthy individuals who might want to have a better way to control a drone or other autonomous vehicles. But most immediately, what we're thinking about are ways that we can help patients who are blind. For example, individuals who have lost the ability to see, what scientists have been able to show is that if I stimulate parts of the brain that are associated with vision, those patients can get a sense of vision even though their eyes no longer work. And so the technology that we're developing now are technologies to stimulate the brain in specific ways. And specifically, we're stimulating the parts of the sensory system so that you can recover a little bit of your sense of vision. And playing that forward to what this might mean for people in the private sector, people in the military, this would be an alternative to your display. And so the idea is that we would have some kind of a helmet that would be able to stimulate your brain in such a way that you would be able to see as though you had a display in front of you, a heads-up display, so to speak, that would be activating the parts of your brain associated with vision. One of the things that has helped us be successful with this program is that Rice has invested a lot of resources in creating a world-class neuroengineering program. So the Neuroengineering Initiative has allowed us to build out new lab spaces where we can bring the people on the team together into one physical location. And students and postdocs can move between the labs. They can develop technology in one space and move next door to another lab where they can test it. And all of these facilities and the excellent people that have come in to join the initiative is really the reason why we've been able to be successful.
Okay, third one is the reason.
Have you ever wondered, is that thing even working? Oh, it just blinked. Red. Is that bad? Should I be worried? Why do we put up with this? Meet Nest Protect. It's designed with advanced technology to sense smoke and carbon monoxide. Can give you an early warning before an alarm.
Heads up, there's smoke in the kitchen.
And if you know everything's okay, you don't have to run around trying to quiet it down. Just hush it from your phone.
Smoke alarm silenced.
Nest Protect tells you where the danger is, so you know what to do and where to go.
Emergency. There's carbon monoxide in the living room. Move to fresh air.
And it can send an alert, so you know what's going on, even if you're not home.
The carbon monoxide alarm is over.
At night, it lights your way. And shows you it's tested its batteries and everything's okay. So everyone can sleep safe and sound. Nest Protect. It's time to know more and worry less.
When you or a loved one has a food allergy, food can be a major source of anxiety, especially when you're not the one preparing the meal. That's where the Amulet can help. The Allergy Amulet is the world's smallest and fastest food allergen sensor. With a small sample of food, the Amulet can detect whether your allergen is present. We've designed the Allergy Amulet so that it fits into every lifestyle. Carry it on a keychain, wear it on a wristband or necklace, or store it in your kid's backpack. The Allergy Amulet's first-of-its-kind detection platform consists of two parts, the Amulet, which is a thumb-sized reader, and a food sampler. Users collect a portion of their food with the sampler, then insert the sampler into the Amulet. Test results then appear on the Amulet indicating the presence or absence of the allergen. You can also pair the reader with our app to track and upload test results, connect with the food allergy community, and send out emergency alerts. The Amulet lets you spend less time worrying, because food should be a source of fuel, not fear.
With the impact of the pandemic on our lives, we have realized the importance of staying in tune with our body's condition. When you're suffering from a headache, cold sweat, or other cold symptoms, you need to take your temperature, but existing thermometers come with inconveniences. That's why we've created HeatCheck, a smart thermometer for modern times. HeatCheck is a compact, non-contact thermometer that plugs into your mobile device. Without the need for batteries or Bluetooth pairing, you can get your body temperature instantly, anytime, anywhere. It's also small enough to take with you, in case you need to use it on the go. HeatCheck utilizes a high-end infrared sensor and a measuring algorithm that has been optimized to measure temperature off the human skin, so that you can get hospital-grade accuracy. With each subsequent measurement, you'll only fall in a plus or minus 0.1 degrees Celsius margin of error. And if the thermometer is too far away, it will send you a vibration notification so that you can consistently get accurate measurements. HeatCheck also comes with an app that will alert you when it's time to take your temperature, and will use your temperature history to help you track and record your menstrual cycle. As you continue to accumulate data on your body temperature over time, you will have the information necessary to keep track of your overall health condition. If your temperature does seem a bit off, there's no need to manually search for healthcare services. The HeatCheck app will automatically show you the nearest hospitals and pharmacies. HeatCheck works with all smart devices that come with USB-C type ports. Attach it directly to your smartphone, store in the cradle, and use the convenient ring holder. This is the new and improved way of measuring and managing your body temperature. Enjoy the ease and convenience that comes with the smart thermometer HeatCheck.
We spend about 90% of our time indoors, and the air we breathe in here is 2 to 5 times more polluted than outdoors. Imagine all the chemicals, dust, and toxic gases trapped in a room with nowhere to go. And the worst part is, we do nothing about it simply because we don't know. Yoo-Hoo is a smart indoor air quality sensor that detects and alerts you of allergens and toxins in the air you breathe. Think of the places you and your loved ones spend the most time in. Do you know the quality of the air in your office at work? In your hotel room when you travel? How about in your own living room or your child's bedroom? These are important because VOCs are found in paint and household cleaning products. Dust can accumulate unseen in fabric around us, and humidity encourages the growth of bacteria and mold. All these cause respiratory problems, skin irritations, and overall poor health in the long run. Yoo-Hoo lets you know when something's not right and what you can do. The simplest and easiest things to do make the biggest difference. Cut down on chemical cleaners, wash your child's favorite toys, air out your living areas, and check on possible gas leaks. Don't leave it to chance or guesswork. Yoo-Hoo keeps track of the air you breathe round the clock so that you and your loved ones get to live, work, and play in the best and safest possible environment. It is the most comprehensive indoor air quality detector on the market today with 8 dedicated sensors that detect volatile organic compounds, dust, carbon monoxide, carbon dioxide, ozone, air pressure, temperature, and humidity.
This is Nest Thermostat from Google. It's a smart thermostat that can help you save energy, which helps you save money on your energy bill. And with all those heating and cooling savings, replacing your old thermostat is almost a no-brainer. You're probably thinking, oh wow, but how? Well, this thermostat can help you build an energy-saving schedule and then adjust automatically, so you don't waste energy when you're away. You just have to select preferences, such as what temperature you like for when you're home, or when you're asleep, or when you're gone, and then plug in your schedule. You know what else is cool? The Nest Thermostat is kind of like an energy-saving advisor. It can help you find opportunities to use less energy. Like it might send a suggestion to tweak your sleep temperature settings, so you can save while you snooze. It can also help keep tabs on your heating and cooling system and sends you helpful reminders, like when you need a filter changed. It can even alert you if something doesn't seem right and help you find a qualified pro for a system checkup or repair, so you can get things working right and go back to living life. And say you're at the park and want to come home to a perfectly cool house. You can go to the Google Home app and take care of that. You can also control the thermostat from your Nest speaker. Hey Google, raise the temperature. Maybe you're thinking, is this fancy thermostat real expensive? Well, actually, it isn't. With rebates from your utility company, you can get it for even less. Oh, and if you like to DIY around your HOME, the Nest thermostat is designed so you can install it yourself, so you don't have to hire anyone to do it for you. But if you want, you can have a pro come install it instead. And that's how you can save energy and money with Nest Thermostat from Google.
Hi, I'm Sylvie, and this is my friend and partner Claudia. We're both serious plant lovers and can't get enough of them. I mean, we really love plants, and we do everything we can to keep them happy. But plants are difficult and demanding creatures. No matter how hard we try, they keep dying on us. Something tragic. Now, how do you keep them alive? Since we don't speak the same language, they can't tell us directly what they need. So we needed to find other ways to connect and came up with another solution. Meet the Phyta Beam. The Phyta Beam is a smart plant sensor that gives plants a voice. It measures soil's moisture, light intensity, the air temperature, and even the soil nutrition levels around your plant. The Beam works with our Phyta app, which we jointly built with experienced plant scientists. The app compares the measurements from the Beam with plant-specific data in our database and notifies you whenever your plant needs something. It literally gives your plant a voice. But the app is much more than just an operating device for the sensor. It's a fun tool to learn more about plants. It will offer you tutorials and other content which will inspire you to take your plant love to the next level. Over time, you will learn to understand your plant without even needing the device. For those of you who travel a lot, we have developed the Phyta Base. The base connects with the beams via Bluetooth and extends the connectivity range of the beams through Wi-Fi. This will help you keep an eye on your plant while you're away. We started working on the Beam over a year ago. Besides developing a highly functional sensor, we wanted to make sure that it is sustainable. We built in a solar cell that supports the battery, and every piece of the sensor can be detached, customized, and separately recycled. But in order to get where we are, we had to go through several iterations. Our first prototypes looked like this, or this, until we produced a functioning prototype. We have already successfully calibrated and tested the prototypes, and the hardware development is now complete. To finish the last mile, we need your help. In order for the Phyta Beam to see the light, we need funds to finance the molds and the first batch. And while the funds are important to us, we're mostly interested in your feedback on how we can improve the Beam.
Be part of our community and connect with plants.
Here at Wise, we believe your home should always feel just right, which is why we're introducing Wise Room Sensor, a little wonder that keeps your home's temperature, as we like to call it, in the Goldilocks zone. Wise Room Sensor works by sharing temperature, humidity, and motion sensing data to your Wise thermostat, eliminating those spots in your home that are too hot or too cold. When you activate Motion Sensing Comfort Mode, it prioritizes comfort in the rooms you're actually using. The more sensors you have, the smarter Wise thermostat becomes at creating the whole home just right comfort feel. It makes your home so enjoyable, your guest just might be overstaying her welcome, because it's just right.
Hello? Is someone there?
Friends, stay in the Goldilocks zone. Get Wise room sensors and make your home feel just right.
Most hosts agree their main concerns are parties, damage, and neighbor complaints. With Minute, you can detect parties before they get out of hand and cause problems for you and your neighbors. 100% privacy safe. Minute sensors monitor noise levels and notify you when it gets too loud. You can easily set custom thresholds, choosing the sound level you think is too loud, including a lower tolerance throughout the night. Minute tracks not just how loud it is, but also how long it is loud for, so you won't get alerted every time a door slams. You can even customize how long the noise has to last before you get a notification, anywhere between 5 and 15 minutes. In the web and mobile app, you will have access to easy-to-read graphs that show you the current and historical noise levels, which can help you fight false noise complaints. You can also automate your guest communication through our Guest Connect feature. So whether you're asleep or just busy, your guests will still be notified if they need to quiet down, either via an SMS or directly through the device, which will start to flash and sound. We even added a tamper detection, so if your guests try to remove the sensor, you'll know instantly. Find out more about how Minute can help you prevent parties, damage, and neighbor complaints at minute.com.
Caring for independent elderly individuals like your parents without the assistance of a home alert system can be stressful. Are they okay at home? Is your dad back from his daily walk? Has your mom finished her shower with no incident? This is where Care Alert from Sensors Call comes in. It looks and acts like an emergency nightlight. Just plug Care Alert into any outlet in the bathroom, bedroom, living room, or kitchen, and it will immediately begin learning about your parents' home environment. Care Alert's AI smarts will continually adapt to your parents' living habits and will alert you if it senses anything unusual in their daily routines. Did their moving patterns change? Was there an unusual change in temperature or in their shower and bathroom visit?
All right. So you may feel some sensors way advanced. This class is not to develop sensors. This class is to use sensor technologies to get the sensor data and display on your cell phone, smartphone apps. Lots of the commercial products is doing the same thing that we want to do in this class, right? So that's what we'll do. Let's start with the easiest one first, LED lights. LED has, not going to go in detail. It has a positive, there's a long leg and short legs. Short leg is like a ground, and long leg, and that is power. So you need to supply the power here, the long leg, and then the K here, that should be grounded. Then you'll get the lights. So LED has colored ones. This is the physics explained. It has a positive and negative regions. So there's electric charges from, I believe, from positive to, from negative to positive. But well, I'm not really sure what is that. But they are moving, right? So current current is moving from one to another, from positive to negative. Therefore, lights can be turned on. That is the same thing. The LED, in the LED technologies, there are two types of the devices available: emitter and receiver. Emitter, therefore, you have the lights. Okay, light is just extra. The LED not originally developed for lighting, but because this is easier and conservative, energy conservative. So now we use LED lights a lot. But originally there's an emitter and receiver. The technology comes from the remote control. You know the remote control at your home? I want you to recall when you were young, or if you are still very young, then ask your parents. In the olden technologies, there's a remote control. Then the front there is some of the light bulb. It is on. Nowadays, if you see the current remote control, there is no lights. Although there is some devices that may emit some waves out, but it's not really the lights turned on. But olden devices, do you remember that, Cheng? Yeah. If you turn this, then you can see the lights on. That is an emitter. And if there is a remote control of your TV set, then in the TV set, there's a receiver that receives that light waves. Depending upon which button that you enter, different signals goes in. That receiver then can allocate different range of the frequencies, and certain frequency comes in, then you can turn on the TV set. Other frequency signals comes in, then channel 1, channel 2, and volume up, volume down. That type of things can be the main, operated. There's a receiver and emitter. We could, but not in this class. But anyway, yeah, because we don't do that sensor itself. IR sensors, infrared detections. Oh, this is infrared detections. Microchips with a photocell that are turned to listen to infrared light. Therefore, we can see this is another type of LED detections. So this tells us the different color, depending upon the colors, depending upon the color. Then we have this is some of the chemical components. This may be a wavelength. So electroluminescence LED foundation discovered by Marconi Round 1907, infrared LED, invented by Robert Beard and Gary Pittman at Texas Instruments in 1961. Visible light, invented by Nick Holonyak at the General Electric in 1962. There's a videos, but let's see what happens.
In the late 1800s, Thomas Edison invented the first commercially viable light bulb. Light bulbs like this work, the video description section. I recommend current will flow into. In other words, you connect the positive side of your power source. Don't worry. For low voltage projects, the backwards LED blocks current from flowing, and it just doesn't turn on. Okay, now let's talk about the forward voltage of an LED. All LEDs need a certain voltage across them in the right direction before any current can flow and they start emitting light. This particular white LED I'm using has a forward voltage of 3 volts, so we need around 3 volts before it can do anything interesting. With the supply set to 0 volts, the LED stays off. With the supply set to 1.5 volts, it's still not enough to turn the LED on. But as we get closer to 3 volts, the LED reaches full brightness. Every LED will have a forward voltage that's a little different, and here's some rough guidelines of what you can expect from different LEDs. Once the LED is on, there'll be a relatively constant voltage drop across it. Next, let's talk about the maximum current limit of LEDs. In this example, I was using a special feature of my power supply to limit the current going through the LED to a maximum of 30 milliamps, which is about as much as this LED can handle. But what happens if I take my foot off the brakes? I'm going to set the power supply to 7.5 volts, and I'm going to remove all current limits. Let's see what happens. So if you significantly exceed the LED's forward voltage rating, massive amounts of current will flow through the LED, and there's nothing to stop it from blowing itself up. Obviously, don't do this at home. It's actually possible for LEDs to explode, sending tiny chunks of plastic and metal flying at your face. You don't want to end up looking like this. Now you see why in my video on voltage, a 9-volt battery was enough.
Impressive, right? Using LEDs, if you build that on Raspberry Pi, you need to do in this way. There's a LED, and then red one's usually the ground, and black, in this case blue, then that is the power supplies. So we have pins there, right? So as you purchase your Raspberry Pi, then there is some indicators for each pins. So which one provides what? Usually this is the top, upper right corner. From there, the third pin, that is I think 5 volts supplied, and then there is a ground. That can be programmed here in Python. So what it does is that you need to import RPI, Raspberry Pi, all for Raspberry Pi, PI, dot GPIO, general pin input and out, GPIO. This is the modules. So let's call it GPIO. Then this module has set mode, setup method, output, input, sleep, that comes from another module, time. So we need to sleep 2 seconds. Set mode. GPIO has 2 kinds of mode, BCM mode and board mode. I'm going to explain that later, but I'm just simply explain to you. BCM mode or board mode. When you purchase this Raspberry Pi, then there is a table comes with it. Then you can see the different indicator for pins. If you want to use BCM, then each pin has a different configuration from board mode configuration. So clearly, literally, you need to say GPIO.BCM or GPIO.board, B-O-A-R-D. And then there is a setup, pin number 4. So whatever the number here, we call that GPIO out. So that can be turned on and turned off. Out. And here, false means, okay, this is a setup. So this pinout number 4 goes to LED's long leg, connected to long leg. What is this? This is the breadboard. Breadboard is nothing but the connection. So rather than directly connected to the pin with this jumper cable, you can simply plug into this breadboard. There's lots of holes. And then in the near, vertically there, if you push the leg of this LED in the same line, if they are in the same line, then they are connected. That is a breadboard. In that way, you don't need to weld, solder the cables. You simply plug in, then they are connected. So this is a breadboard. This is a jumper cable. This is LED. LED here and Raspberry Pi. This number 4 goes to this blue line, the pin out number 4. And then we can say here output. True means we supply power. False means cut off the power supply. So we turn on this LED and wait 2 seconds and then turn off. That's what this code can do. This is a very simple code, but we need to start from this. So actually what we need to do is we need to wire using jumper cable. So everything needs to be wired between your Raspberry Pi and the device, LED. In order to wire in an easy way, we need to use a breadboard so that they are connected. When all the wires complete, then we need to do scripting. Python script. This is an example of a Python script. And then you can run that Python. Then, as you programmed here, LED first turned on, and 2 seconds, and turned off. Basically, this kind of sequence is the sensor controlling. So another type of sensor is a photocell. Photocells. So it can tell us whether there is a light or not, right? We have here squiggly faces. This can take the lights, right? How much light is shining onto a squiggly face. That is what this photocell indicates. For example, in the light along the streets, when sun goes down, then lights is automatically turned on, right, on the streets. There is a sensor. That sensor is called photocell sensors. So when there is no lights, see here how much light is shining. So there is some calibrations. Not enough lights shining. Then actuation is what? Turn on street lights. That's what the sensor technology is doing. That has been done many, many decades, right? This is what it is. Some of the physics. Motion sensor, motion detections. There are also passive motion detection and active motion detections. In this case, passive motion detection comes from, if you want to check the living body motions, then passive IR motion motion sensor works. Living objects. What that means is that living objects emits the temperature out. Therefore, that temperature is received by this PIR motion sensors and doing further. If there is active sensors, active motion sensors, then it can also, you can see the difference between, for example, if it is active, then generates some of the waves, and this is not living objects, but maybe metal or vehicle. Vehicle generates the fever, I mean the temperatures. But let's say some weapon is moving. Then that comes here, that cuts these waves. And then there is another waves there's some intervals. So cut another. Then these objects, when this was cut, then this object was in this position. And when this wave is cut, then this object in another position, which there is some distance. What that means is that that object moves, right? That is detected. That's active motion sensors. Two types of sensors are available. These motion sensors, this is very cheap. You can test this. So I am maybe next we will do real hands-ons with Raspberry Pi next week. So bring your Raspberry Pi, then we need to configure the Raspberry Pis. We need to set up Linux. We call that Raspberry Pi operating systems, which is kind of Linux. Configure it, and then we need to we need to set up Wi-Fi. So it is like a computer. But as you looked at the Raspberry Pi does not have any input and output device. No input device, no output device. Only the brain there. The input, then you need to have a keyboard, mouse. There's a USB ports available. To visualize it, you need to have a screen, terminals. You can buy extra small terminals, or you can, if you are working at home, then you can use TV sets. TV sets is the HDMI connectors, right? As far as there is a HDMI connectors, you can connect it to your Raspberry Pi. One time, we can use that external display, but we can use our laptop for the display of that Raspberry Pi. But in order to set up that configuration, initially you have to see that Raspberry Pi's terminals. So here in this classroom, we have that somewhere there you can use some terminals if you have HDMI cables. After you configure it for laptop display, then you can use your laptop displays after that. But initially, you have to set up by looking at Raspberry Pi terminals, so that you can put that some command, and then you can set up also your laptop, so they need to talk each other. Anyway, this is inside here in this sensor, motion detection sensor, and you see some of the different angles, multiple different, like a lens, so that it can detect. What it does is that you need to sense the position of these objects from one position to another positions. Therefore, it identifies the motions. It could be passive, could be active, but this one, cheaper one, that is passive, PIR, motion sensors. I think this is maybe a couple of dollars. If you want to do motion sensors, then like here on this Raspberry Pi, this is just an indicator, LED. And also we have here resistor, somehow here, I'm not sure. Usually we put a resistor for these LEDs. Remember that on the video, if there is a high power comes in, then your LED burned out. Therefore, in order to resist that unreliable power supply, then we have a resistance, okay? Small electronic devices. This is extra. This one has nothing to do with motion detections. Here is a motion detections. In this motion detections, if you see here, this LED is just indicator. Motion sensor it has only one pin, pin number 4. And we have, depending upon this motion sensor, this motion sensor probably has some of the packages. We do not use these packages, but this is a simple, the example of the configurations, the codings. So we need to identify which one is what. For example, pin number 17 for LED, and pin number 4 for motion sensor, and then this is the main body of our codings. While true, so we continue to do this, and then this PIL, this is not complete, right? Somewhere there's a PIL needs to be defined. Oh, PIL here. Motion sensor. Motion sensor is a PIR. The motion sensor has the method. We don't really define method for this. We simply use it. Okay? So depending upon the sensor that you purchase, there is the method available. So wait initially, and then green light on for LED. Oh, this continues. So if wait until motion is detected. If motion detected, then motion detected. And therefore lights on. And then and then we have to off. Wait for no motions. Motion stopped. This is a looping. This goes continually, forever. So output could be detected and stopped, detected and stopped. This is output. This is an example of coding, scripting. This is an example of wiring. This is an example of running. This is a good guideline for you. You can picture it, but as we do really hands-on, then you may be able to see it clearly. Distance sensor. There are two types of distance sensors available: ultrasonic distance sensor or laser distance sensor. Laser distance sensor is expensive and is really accurate. It's called the LIDAR, so-called the LiDAR, but we are not going to use this, but ultrasonic distance sensors. The model usually HC-SR04. And it works like this. I have some sensors available, so I may let you use some of the sensors I may bring. I'm not sure which ones are available right now. I'm sure a couple of these available. So how can we measure the distance? Distance sensor is usually active sensors. So what it does is that if you see here the pin, there is a so-called trigger and echo, and there's 4 pins available. 2 pins for signals, and 1 pin for power, and the other pin for the ground. So 2 pins. This is not, it depends on the real device. So when you see real device, then you need to take a look at what is what. So in this case, the trigger, this trigger the signals, and when there is an object, then reflect from there. So you have an echo signal and trigger signals. Trigger signal and echo signals. There's a time interval until you receive echo signals. This is ultrasonic sensor. Remember that in your maybe middle school physics, our voice can traverse 340 meters per second, right? Our voice. That's average. Depends on person. Some person may shout loud and clear, stronger, then it travels fast, right? My voice, old guys, maybe slow, right? Ladies screaming, maybe so fast if you're screaming, right? But anyway, average speed is 340 meters per second. That is the velocities.
You said the 4 pin, right?
Yeah.
4 pin, 1 is trigger, 1 is echo, 1 is power, right? And
You're talking about this, right? Yeah, 4 pins, 1 pin for triggering, the other pin for receiving. There's echo.
And the
third one is the power, and the last one is ground.
But the echo pin, it is only recognize the trigger pin.
Right. In real codings, yeah, we get the data from trigger pins and echo pins.
It can't to recognize the normal sound like
No.
Right.
Only. It's not really sound. But frequency is in the sound frequency, we call it. That's ultrasound. Because this is ultrasound, we cannot hear. That is above, beyond our acoustic sound.
But is it the ultrasound is from the trigger pin, it is always keep sending.
Yeah, keep sending.
Keep sending all the time, and the echo pin is just waiting.
Right.
Until
But we will have to control that on our codings. If you look at here, we set up and then GPIO output we trigger high, which means we send out. This and this are the same statements. We send out and wait, send out, and then we don't do anything. And then send out and then stop. What it does is that we send out for this duration. How many seconds? 0.00001 second. That short time period, we emit, we send out trigger signals. And then we stop trigger signal here. This is a stopping trigger signals. And then we need to see if there is echo signals. If we have echo signals, then we measure the time. Sending out, and then that signal comes in, then we see the time difference. If we have 1 second, then it is 340 meters away. 2 seconds, then 680 meters away, right? If there is half a second, then 170 meters away, like that. That is our measurements. That is the physics. Okay. So in this case, we need to see if this is 1 second, then that is a round trip, actually, right? We check the time here, and we check the time when that echo signal comes in. Then that time elapsed is a round trip. Because it starts from this to this object and coming back, round trip. So we have to divide that half. If it takes a half seconds, then it is not 174 meters away. We have to cut half again. So maybe 80 meters away. That's what we do here. Okay. Pinout for Raspberry Pi. If you purchase the Raspberry Pi, then you will get this kind of the indicator, the card. There's a numberings. See here, this is numberings. Left 2 columns, right? So numbers 1, 2, 3, 4. If you follow this number on your coding, then you need to say, hey, I'm going to use GPIO.board mode. If you use outside number, this number is not indicated if we use PCM. Only voltages, ground. All others, there's a number, GPIO number 2. So if you say this is a GPIO number 2, then that is a PCM mode. If you want to see this pin for GPIO 2, then you need to set the mode PCM. Unless otherwise, this pin number is 3. That is what we need to do. This PCM is well designed for example, some of the communications, CLK, MISO, MOSI, and also TX, RX, UART communications. This is probably SPI communication, general purpose interface communications, while all the wireless communications. If you want to do something using this Raspberry Pi to communicate other devices wirelessly, then because the PCM mode already has some pins designated for SPI communication or UART communications. Here SPI communications, CE signals, GEN, MOSI, MISO, CLK. Probably you guys don't have that the knowledge yet, right? If you take some of the courses about wireless communication, then you may be able to know about this. UART antenna, then it uses a transmission and receive and transmission signals. Then you need to use these two pins by setting PCM mode, or SPI, or C square I communications. They're all different. Wireless communications, if it is a wireless communication, then you need to have a different antenna in it, right? So depending upon the antenna, you have a different pin out to be wired. So LiDAR, this is real advanced ones. Light detection rangings. LiDAR sensor fires off beams of laser lights and then measure how long it takes for the light to return to the sensor. This concept is exactly the same as ultrasonic distance sensor devices. LiDAR and ultrasonic distance sensors both are under the same physics concept. LiDAR tech principles. If you want to watch the following for fun videos, watch the following videos. 3 minutes and 19 seconds to 4 minutes and 15 seconds. If you want to see distance uncertainty and beam diversity, and look at that. Very deep levels. So this is technically deep. This is for fun. Which one that you want to watch together here? Fun or tech intensive? Tech intensive? Okay, let's see what.
Hello and welcome to this Automotive IQ webinar by Hamamatsu. Before we start, we have 3 questions we'd like to ask our audience, so please take 10 seconds per slide and give your input.
Speed of light times the pulse duration.
This is tech intensive.
Here, let's now discuss timing of our LiDAR. So first, I would like to point out, facing an engineer designing time-of-flight LiDAR, photo detector, will not be able to perhaps
this is a tech intensive.
Comes from the electronics, from the resistor.
You understand? Let's move to fun.
LiDAR, light detection and ranging. LiDAR is a remote sensing method that uses laser to measure elevation like ground, forest and buildings. LiDAR uses ultraviolet, visible or near-infrared source to sense objects. Light energy emitted by LiDAR system is known as pulse. Light reflected from ground or object is known as return. This means the LiDAR system sends a pulse of light and it waits for the pulse to return. It measures how long it takes for the emitted pulse to return back to the sensor. In the end, it gets a variable distance of the objects. Actually, this is how LiDAR got its name: light detection and ranging. Like sonar uses sound waves to map things, radar uses radio waves, a LiDAR on the other hand uses light sent out from a laser. A LiDAR unit scans the ground from side to side as the plane flies. Because of this, it covers a larger area. While some pulses will be directly at nadir or a straight line, most pulses travel at an angle. Airplanes, unmanned aerial vehicles, and helicopters are the most commonly used platforms for acquiring LiDAR data over broad areas. There are different ways to collect data using LiDAR: from ground, from plane, or from satellite. There are three types of LiDAR. Topographic LiDAR. It maps the land typically using near-infrared light. Bathymetric LiDAR. It uses water-penetrating green light to measure seafloor and riverbed elevations. Terrestrial LiDAR for mapping buildings, natural features, and trees at ground level. It is also very useful for 3D models of heritage sites. How does a light detection and ranging system work? There are 4 parts of an airborne LiDAR. LiDAR sensors scan the ground from side to side with a pulsed laser beam as the plane flies. The sensor has a detector for sensing the returns from objects. GPS receivers track the altitude and location of the airplane. These variables are important in attaining accurate terrain elevation values. Inertial Measurement Units, or IMU, tracks the orientation and speed of the airplane as it flies. Elevation calculation use orientation to accurately determine the actual position of the pulse on the ground. Computers record all of the height information as the LiDAR scans the surface. These 4 parts of LiDAR system work together to produce highly accurate and usable results. LiDAR is used for wide area mapping, coastal changes, floodplain mapping, and for engineering applications like for mapping bridges and roads. LiDAR system allows us to examine both natural and man-made environments with accuracy, precision, and flexibility. In the next part of the LiDAR story, we talk about the various uses of LiDAR in detail. Keep watching.
So laser types of frequencies, this is really wide ranges, right? So far, IR, X-rays, from IR range to laser signals can cover these wide ranges, so that we can use that particular the videos using the signals in this range of the frequencies. But if we use X-rays, then it goes communications with satellites or space shuttles, so longer types. This is LiDAR light versions of a sensor that is available also. You can take a look at this. Temperature sensors. This is a typical temperature sensors is well known. I think this is it. A lot more sensors available. we do not cover. We cannot, right? We have only one sessions covering sensors. Next week we will do Raspberry Pi. So after this class, I'm going to post some of the videos how you can configure Raspberry Pi, all related with the Raspberry Pi that I recorded earlier, so that still valid. I'm not sure how many video clips. I think about 3 video clips available. So I will post it. When you have time, please watch it. So you may be able to see what you want to buy. Minimum, you need to have Raspberry Pi and extra mouse and extra keyboard if you have a small keyboard available, or whatever. There's some rollable keyboards available. Simple. That way you can type. And monitor, if you have a small monitor that has HDMI connections, you can bring it. But we can use some of the monitor here, the board. I'll let you know how you can use, as far as you have HDMI cables. One end, it should be the regular HDMI, and the other end depends on your Raspberry Pi. Usually your Raspberry Pi, if that is model 4B, there's a current version, then I think there's a mini, small ones. One side, the small ones. Oh, I think there's a USB-C type. No. I think mini. Different.
The ones that you recommend on the website, Amazon? Can we buy those?
No, it depends on your Raspberry Pi. Usually, my tip is that if you buy bundle kit, that comes with the right version of HDMI. Okay, if you buy separately, then very hard. Look at this. If you go to Amazon, then kit, if you say kit, then this is a Raspberry Pi here as an example. I mean the HDMI. This HDMI, see here one side, one end that's regular. If I move this, then it goes away. There's here one end that is a regular port. The other end that is a micro or mini. This is needed HDMI, and this the memory SD card. 32 gigabytes SD card is enough. There are 1 gigabyte SD card available also. Then that is about $100. So 32 gigabytes, maybe $10 if you buy separately. And this is needed also in order to this is a USB. You need to plug this SD card in it, and then we can program it. After we install Raspberry Pi operating system on this SD card, so we have to do that on our laptop. Configure it completely. If it is done, then take out this SD card only and plug that SD card at this end. behind this board there is a slot for this SD card, and then we turn on. This is a power, or this is HDMI. This is a power. Power line is a USB-C type power line. So this is a power. One end of this power goes to this Raspberry Pi, the other to the wall. Oops. Why? Okay, here. No. We don't really need this case. We don't really need this ventilizer. But we needed this, the physical ventilizers. So this is, I think this is CPU. This is maybe communications. Well, CPU and communication that heats up usually. So we put this ventilizer panels here so that it can cool down. This is for camera. This is for audio. You have two USB, two stacks. So actually 4 USB connection port available. This is for Ethernet port. If you connect this directly to your router using Ethernet cables, you can do that. If you set up a network intensive project here, these are the pin numbers, 40 pins available. Some of the memories, I think this is some of the memories. So the range of memories available for this current the Raspberry Pi is 2 gigabytes, 4 gigabytes, and 8 gigabytes. Depending upon the configuration, you have a different chip layout here. So this is needed. This is for SD card when you set up Raspberry Pi operating systems in it. This is actually one time we use. Once it is complete, then we don't really need this. But because of a one time, then we need this. SD card, definitely needed. HDMI, again, this is one time at least. HDMI, when we do configurates. And if you want to connect to your laptop, then we don't use this. Another kit, different combinations, right? Yeah, they're all the similar ones. These are some sensors. Some very expensive. For example, this is 8 gigabyte RAM. RAM size, as I said, you don't need 8 gigabytes. If you have a cheaper price for 2 gigabytes, that'll be enough. This is 4 gigabytes, therefore it is over $100. 2 gigabytes.
In that link, it had 3 options in the link.
Oh, in this
Yeah,
this one?
The
Oh,
one is the gigabyte.
the other one is cheaper.
Yeah, the top, the bottom, yeah, the first one. No.
Oh, here.
Yeah, yes.
This is 2 gigabytes, 4, 8. Oh, not much difference in price. Yeah, as I said, you don't need the 4 gigabytes. 2 gigabytes is enough. Oh, this comes with that. These are the sensors, right? Oh, we have lots of LEDs. This is for the cables, and we need. Is there bread? Yeah, here bottom breadboard, and some LCD. Some of the touchpad if you want to emulate some of the projects. We have here jumper cables. Yeah, this is the motion. This is a distance sensor. Motion detection sensors. Yeah, this. Where is the motion detection? There is no motion detection sensor. Let's see. There's another. Yeah. There's no other suggestions. Not. There are lots of combinations available. Different combination, right? We don't really need these many. Oh, here this is, yeah, this is a distance sensor, motion detection. This is distance, and some other sensors available. So many others, if you are interested in. This is RFID keypad. This is a RFID card. I think this is a RFID reader. If you want to do this project, so you have to see what you want to do. Do not spend big money. Small. Let's see if there is small ones. Yeah, this is cheaper than the other. 2 gigabytes RAM. It has everything. Oh, even cheaper. Visa Raspberry Pi 4 Model B starter kit, 1 gigabyte. I'm not sure this is real Raspberry Pi. I think this is not genuine part. Similar, but not exact, not the genuine. Well, this is a lots of good ones. We have a breadboard. I think this is a transistor. We have some resistor here, resistance, and jumper cable. LEDs. Switch. Not much sensors. So it's up to you guys. If you are interested in working on this even further for your master's project, you can invest a little bit more, acquiring better sensors if you want. Other than that, minimal, okay? Cheaper ones. But Raspberry is must. Raspberry Pi. Others, optional. Any other questions?